Last time we were together and we talked about section 11.4, we were dealing with tree diagrams. And when I started off that section, I said the reason we're doing this is because as we started out talking about probability, our focus has been on what is called a simple event. Now remember, the word simple in math doesn't mean easy. It just means less complicated. Okay, so simple events mean only one thing's happening. So when I pull a card from the deck, I want to know the probability it's a heart. Or if I roll a die, what's the probability it's a 4. And so then when we got into section 11.4 and talked about tree diagrams, we began kind of broaching the idea of a compound event, meaning where more than one thing or more than one possibility is happening. So this begins to make probability look a little more realistic. And we could, if we had enough time, we could do a whole semester on probability, but we're only doing 8 sections, so we don't get too deep into it. So we're going to talk about 2 types of compound events. We're going to talk about events that are joined together with the word or, and we're going to talk about events that are joined together with the word and. Okay, so first we're going to deal with or events. Now, the key when we deal with an or event is we're doing one thing. Okay, so we're drawing one card or we're whatever our experiment is, we're performing it once, and we want to know what the probability of this or that, event A or event B happening. So when I go to find the probability of event A or event B, this is the way I do it. I do it by, to determine the probability of event A or B, we use the following formula, and it goes like this. The probability of event A or event B happening is equal to, the first part of this seems very, I think, very intrinsic. The probability of event A plus the probability of event B, you just separate them. And then what I have to do is then subtract the probability that these 2 things can happen at the same time, that they can happen simultaneously. I don't know that I can spell simultaneously today. I always want to use the wrong vowels in words. Now, I'm just going to take us into the past just for a moment. If you remember when we were talking about sets, so this actually isn't bad review because in like 4.5 weeks, we got a final exam coming up. If you remember, we were doing our Venn diagram. So here is my Venn diagram. Can you see that on the screen? Yes. And so we have this, and here is set A, and here is set B. Hopefully I'm jogging some memory. At the time, we talked about the idea of being able to find the number of elements in the union. Remember, the union is what you get when you glue both sets together and you're taking everything in both sets. So we answered this question: how do we find the number of elements in A union B? And the reason I'm bringing this up is there is a lot of overlap between sets and probability that we're not talking about, but this is the one area that we will notice it most. That when I go to find the number of elements in set A, here's how we did it. We found the number of elements in set A, so I'm going to just use some shading that goes down and to the right. Then we added to it the number of elements in B, and I'm just going to do some shading that goes down to the left. And notice by my shading, what have I double counted in that drawing? The middle, the intersection. And we talked about this back at the time, and we had a great time talking about it as you were just getting to know me. So we subtracted the number of elements in the intersection, the things that happen in both sets. So you can see how similar this formula looks to our probability formula. It's based on the same thing. Okay, it's based on when I find the probability of A or B happening, I'm going to find the probability of A. I'm going to add to it the probability of B. So I'm just going to find the 2 things separately. Then I'm going to subtract when they happen at the same time, meaning the intersection of the 2 events. Okay, so we're just going to do a lot of practicing. Okay, so that you can get your, that you can wrap your mind around this. Whatever questions you have about or events, please be sure to ask. I'm 100% here for you. So example 1 is my example. It says 1 card is going to be selected from a standard deck of playing cards. We're going to determine the following. I'm going to do the A part, and then you're going to do the other part. So the A part here says, what's the probability of an ace or a 9? Well, for these first 4 problems, I'm going to write this all out just as we get used to doing this. So what this is going to be is it's going to be the probability that I select an ace plus I'm going to find the probability that I select a 9. And then I'm going to subtract the probability that those two things happen together. Now, I did not reprint the slide of the deck of cards. So if you have that on your notes, if you need it, that's fine. So how many aces are there in the deck? What's the probability that I choose an ace? Yeah, there's 4 aces. Remember, there's 4 of each type of card. They're all a different suit. There's 2 different colors, and there's 52 cards in the deck. So that's kind of the basic information that you'll need for these first four quick examples. Plus, what's the probability that I draw a 9 from the deck of cards? Okay, again, 4 out of 52. Now, don't be worried. On the test, I will give you the picture. I just forgot to attach it on this sheet. And then I'm going to subtract. Are there any cards that are both an ace and a 9? No. Okay, there are no cards. So that's 0 out of 52 that they happen together. And so 4 out of 52 plus 4 out of 52, the nice thing is I'm not reducing those fractions. So the denominator is the common denominator. So 4 plus 4 is 8 out of 52. And just to refresh your memory, you can either reduce that fraction or you can make a decimal, which I'm going to do just because it's easier. And so I get 0.1538 as my probability. Now you'll notice I picked this first example intentionally. You'll notice that the probability was 0 that these two things can happen at the same time. And so this is an example of what's called a mutually exclusive event. Mutually exclusive means that you have events that cannot occur at the same time. So if you've ever used the words mutually exclusive, or if you've ever heard those words used, what they imply is that the two things being talked about cannot happen at the same time. Okay, 2 things are mutually exclusive if they can't happen at the same time. All right, once you've written that down, we're going to do these one at a time as we get used to doing this. Please do problem B. I will give you a little hint that problem B is not mutually exclusive. Okay, there will be an intersection for you to think about. All right, let's try this one out, see how you did. If you've got any questions at all about doing an OR event, please bring them on. So the probability of to find the probability of an ace or a heart, I first have to find the probability of an ace. Then I'm going to add to that the probability of a heart. Then I'm going to subtract from that the probability that those two things happen together. So we already did the probability of an ace. There are 4 aces out of 52, so I'm going to write that down. Plus hearts. How many hearts are in the deck of cards? There are 13, yes. There are 4 suits. The hearts are one of the suits. So there are 13 of each of the suits. Then minus, how many cards have both an ace and a heart on them? 1, the ace of hearts. Okay, yes. So that's 1 card out of 52. And so now when I do this, 4 plus 13 is 17. 17 minus 1 is 16 out of 52. Again, you are welcome and most welcome to go ahead and do the reducing of that. But I think if we go ahead and divide, we're going to get 0.3077. We're doing all right. Anybody got a question for me? All right, then go ahead and do the next two. Go ahead and give those a try. One of those is mutually exclusive. The other one is not. Spoilers. All right, so the first one is I'm finding the probability of a red card or a black card when I draw this one card out. So I'm going to find the probability of a red plus the probability of a black minus the probability those two things happen at the same time. So how many red cards are there in the deck? Yep, 26 out of 52. How many black cards are there in the deck? Yeah, that's for sure. And then how many cards are there both colors? 0. This is mutually exclusive. The cards are either one or the other. So 26 plus 26 is 52 out of 52. And so that is a probability of 1. Just remind me, because it was one of the basic probability facts from long, long ago. A probability of 1 means what? 100% has to happen. It's certainty. When somebody hands you a deck of cards and says pick one, you know it's going to either be red or black. There's no other options as far as that separation. Okay. So the next one is the probability of a picture card or a red card. So again, we're going to do the probability of a picture plus the probability of a red minus the probability of a picture card that's red. So how many picture cards? Does anyone remember? Yeah, there's jacks, there's queens, and there's kings of each suit. So that's 12. Again, when you take the test, I will give you the picture of the cards. You do not have to stress about memorizing that. And then plus how many red cards? Well, you just told me. You don't need to tell me again. So that's 26 out of 52. Minus how many cards are there that are both of those things? Yeah, there's going to be 6. There's going to be hearts and diamonds of each, the jack, the queen, and the king. And so then 12 plus 26 is 38. Minus 6 is 32 out of 52. And when I pop that into the calculator, I end up, and you should end up with 0.6154. I got to squeeze that in. I didn't leave myself a great amount of room there. Is this making sense? Are we doing okay? All right, well, I've got just, I'm going to switch up the deck of cards. This is just a picture from the book that I copied and pasted just to create some different examples. So what I would like you to do, and if you need help, wave your hand. I will walk over to you. I want you to leave here, feel nice and certain. Go ahead and do those 5 problems on example 2. I'm going to give you 4 or 5 minutes to go ahead and do that. Anyone have any needs? Okay. Okay, about another minute. Do as much as you can, and then whatever questions you have. These will be our last OR events, and then we're going to talk about the other type of compound event for the day. So any questions you have, again, bring them to the forefront. I still see a bunch of people moving, working, so I'm going to give a little more time. I don't want to ride anybody to feel rushed on this. Okay, so if you're missing any of these probabilities, just let me know. Okay, I wanna make sure that we leave here pretty clear about this. So the first one is the probability of a lion or an even number. So again, I'm not gonna write out the whole formula, but I'm gonna find the probability of each of these things separately, and then I'm gonna subtract the probability that they happen together if they can happen together. So first, the probability of a lion. Will somebody tell me, what's the probability that if I close my eyes and pull a card from this deck, it's going to be a lion? Yeah, there's 5 lions out of the 20 cards. Great. Plus an even number. Same thing. What's the probability of an even number? Anybody struggling coming up with those values? Okay, that's just each of those is just the basic probability problem from section 1. That's why I mentioned back then it was so important just to get that homework nailed down and feel pretty good about it. Okay, now minus. Do these two things happen to get together? Do I have any lions with even numbers on them? Yeah, there's 2 out of 20. Great job. And so when I do that, 5 plus 8 turns out to be 13. 13 minus 2 is 11 out of 20. That is a reduced fraction. You can leave it just like that, or you can pop it into your calculator and it becomes 0.55. So far, so good? All right, well, I'm just going to do the next one then. Probability of a yellow bird or a number less than 3. Okay, sounds great. So when I go and do this, what's the probability that I draw a yellow bird from the deck of cards? That's great. There's 2 yellow birds out of 20. Great. A number less than 3. How many cards have a number less than 3? Yep, that is indeed true. Minus, are there any yellow birds with a number less than 3 on them? Yep, there's 1. That's just top left-hand card, 1 out of 20. And so then 2 plus 8 is 10, minus 1 is 9 out of 20. Again, that is a fantastic, perfect, lovely answer. Or you can pop it into your calculator if you're partial to decimals and get 0.45. Anybody struggling with this? Am I going too fast? Okay, I'm not getting any feedback, so I'm just going to keep going. You let me know what you need. The probability of a lion or a 3. So lions, you've already told me, are 5 out of 20. What's the probability that I pull a 3 out of this deck? Okay, 4 out of 20. And then do lions and 3s happen together? Yeah, right here, right in the middle, 1 out of 20. So 5 plus 4 is 9, minus 1 is 8 out of 20. You can reduce that. That would reduce to 2 out of 5 if you want, or you can just pop it into your calculator and it's going to be 0.40. Red bird or even number? Okay, here goes. The probability that I select a red bird, how many red birds are there? Yep, and then you've already told me about even numbers. Even numbers from the part A are 8 out of 20. And then do any red birds have even numbers? Yeah, just 1 of them. Perfect. And so that is 3 plus 8 is 11, minus 1 is 10 out of 20, and 10 out of 20 just becomes 0.5. Last one, yellow bird or a frog. So you already told me that the probability of a yellow bird, you told me that in a previous problem, was 2 out of 20. And then what's the probability of a frog? Now, there's 5 of them out of 20. You're doing great. And then minus, do yellow birds and frogs happen at the same time? 0. So this is yellow birds and frogs are an example of what kind of event? Mutually exclusive. Great, remembering the terminology. So 2 plus 5 is 7 out of 20. And then again, that's reduced. You could leave it. There's no need to do any more. So again, remember, you only need to give me one of the formats of the answer, either a reduced fraction or a decimal. You do not have to do both. Okay, I'm just giving both because I'm partial to the decimals, but it really does not matter. That is or events. Do we have any questions before I move on to and events? Okay, now here's the thing that I want you to know about the and events. The and event we're about to talk about is different than the and in the probability of the or event. So I just want to repeat to you, when we do these or events, Okay, this is the simplest type of OR event. Okay, there's more complicated things. We're not going to talk about them in this class. So our OR event is I am doing one thing. In each of these problems, we pulled one card. And then we looked at that one card and could those things happen at the same time? So this is simultaneously, meaning do these two things happen at the same time in my one event? Now down here, when we talk about this type of AND event, our book puts these in the same section because they're both very short to deal with, but I don't want there to be any confusion. This AND, when I'm now going to find the probability of A and B, what we're talking about now is when I'm doing two or more trials. So like I'm drawing two cards out of the deck of cards. I'm going to roll two dice. I'm going to spin the spinner twice. Anything that I do that I'm going to do more than once, now we're going to do as an AND event. And so the word AND has the implication, it implies and then. So when we say we want to find the probability of A and B happening, what we're really meaning is the probability of A and then B happening. Okay, so there's more than one thing. Are you tracking with me? I'm trying to make a big deal of it because I don't want there to be any confusion when I put these on a test, and I don't want anybody to get the ands confused. But once you get that straight, for your basic AND event, finding the probability is a pretty relaxed thing. The probability of A and then B happening is just equal to the probability of A happening times the probability of B happening. It's based on the counting principle that we talked about in the section last time. So here's my example down at the bottom of the page. I'm going to do this one. It says two cards are selected with replacement. I'm going to underline that, making sure I'm reading good. Let me just call timeout. I'm pausing the problem. When I tell you that I'm drawing two cards with replacement, that means after I pull the first card, what am I doing? Putting it back. It can be selected again, okay, with replacement. So two cards are selected with replacement from the standard deck. Find the probability of two diamonds. Okay, great. So the probability of two diamonds means I'm finding the probability of a diamond and then a diamond. Okay, I'm just rewriting it differently so you see how this applies. Doing this with replacement. So here goes. When I close my eyes and I pull a card from the deck of cards, what's the probability that the first card is a diamond? There are 13 diamonds out of the 52 cards. Fantastic. That is beautiful. Times. I'm doing this with replacement. So I look at that first card. It's a diamond. Yeehaw! I put it back in the deck. I shuffle it again, and now I'm going to pick again. What's the probability that the second one is a diamond? Same thing. Great, 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 great. Love it. Now, at this point, what I would do just to keep things as easy as possible is I'm just going to use my calculator to calculate this. So I'm going to go over here and I'm going to go, okay, 13 times 13 is equal to 169 divided by 52 divided by 52 again, and that's going to be 0.0625. If you want to use the fractions, that is totally fine. My suggestion to you is reduce first before you multiply. It's going to make life a little easier. So what I mean by that is, okay, 13 out of 52, 13 goes into 13 once, 13 goes into 52 4 times. The same thing over here. And then in the tops, 1 times 1 is 1. 4 times 4 is 16, and there's your reduced fraction answer, which is the same thing as 0.0625. Okay, so whatever makes you happy. Are you with me on how we did that? Because you're going to repeat this exact problem, example 3, except you are going to do it without replacement. That's the problem at the top of the next page, example 4. I want you to find now in example 4 the probability of 2 diamonds, but this time you are not replacing the card. Okay, I know this can be a difficult thing. So if you got this first one wrong, give yourself permission and grace, learn, and then you can fix any problems when we do the next examples. Okay, so the probability of a diamond and a diamond. This time I'm doing the problem without replacing the card. So I reach my hand into the deck. The first card being a diamond has a probability of 13 out of 52. You already told me that. But this time I see that it's a diamond. I'm going to stick it to my forehead, or I'm going to put it in my pocket. I am not putting it back in the deck of cards. So now when I reach my hand in the second time, how many diamonds are left in the deck? 12 out of how many cards? 51. There you go. Again, if you missed that, it's okay. You're learning. But let me ask you this question just to prepare us for the future. Let's say I asked the problem that we were going to draw 3 cards. And so now I've picked the first one, 13 out of 52. The second one, 12 out of 51. Now I'm still without replacement. I reach my hand in again. How many diamonds are left in the deck for the next one? If I had 13 diamonds the first time and then I pulled one out and then there's 12 diamonds and now I'm pulling another one out, how many diamonds left for the next one? 11 out of how many cards? 50. So if I said, what's the probability of 3 diamonds? Then you just do it again. Okay, that wasn't my question, but I just wanted to cover that possibility. So here I've got 13 times 12, then I'm going to divide by 52, then I'm going to divide by 51, and that's going to turn out to be 0.0588. So the reason I had to do the same thing, but with replacement and without, is I wanted you to see the difference between these two events. Independent events are 2 events. Okay, so 2 events are independent. Two events are independent if the first one occurring does not affect the probability of the second one. Okay? So 2 events are independent if the first occurring does not change the probability of the second. And example 3 at the bottom of the previous page, that was an example of independent events. Example 4 that we just did, notice when I drew a diamond, the first event happening, that changed the probability of the second diamond. So those would be called dependent events. When the probability does change, the events are called dependent. Okay, so what I would like you to do next is, if you have any questions, of course, do that. But if you don't have any questions, you're going to use the deck of cards from the previous page, those 20 cards with birds and frogs and lions and monkeys on them. And you're going to select 2 cards. Okay, we're just going to keep it at 2 cards. And this first go around, you're going to do all of these problems with replacement. So I'm going to give you 2 or 3 or 4 minutes. I want you to do these 4 problems with replacement using the deck on the previous page. And if you need me, wave your hand. I'll come to you, give you all the help I can. That's the first card. Replacing it, so now that's the probably the second one. What is it? All right, so for example 5, here we go. I'm going to first do the probability of 2 3s. So when you look back on the previous page, what's the probability that I draw a 3 from that deck of cards? Okay, there's 4 3s out of 20. We're doing this with replacement this first time around. So now I'm going to draw another card. What's the probability? The second one's a 3. Yeah, that's excellent. 4 out of 20. So when I multiply those together, 4 times 4 is 16, divided by 20, divided by 20. What is my final result there in the calculator? 0.04, is that what you said? Great, thank you very much. All right, so now the probability of a lion and then a monkey. Okay, fantastic. Well, what's the probability the first time around I draw a lion out of the deck? 5 out of 20. And then I replace that card. What's the probability then that I draw a monkey out of the deck? Yeah, excellent. So 5 times 5 is 20. 5 divided by 20 divided by 20. What is that decimal? 0.0625. Did I hear you right? Okay. Frog and then a yellow bird. Well, I'll give you the frog because there's the same number of frogs as there were lions and monkeys. There's 5 of them. And then I replace that card. What's the probability of a yellow bird with the second one? 2 out of 20. So 5 times 2 is 10, divided by 20, divided by 20. What does that decimal become? Is anyone having trouble coming up with these numbers? If you didn't get the first time around, do you see where it's coming from? All right, well then what's the probability both are even numbers? So what's the probability I draw an even number out of this deck? Okay, 8, there's 8 of them, so that's the same thing twice. And so then 8 times 8 is 64 divided by 20, and then divided by 20, that decimal turns out to be 0.16. Great. I feel good about that. I want you to feel good about that. We've got plenty more that we're gonna do. In fact, example 6 says what you're gonna do now is you're gonna do the same 4 problems, but this time you're gonna do them without replacement. So I'm just gonna draw a little wall right here. I'm gonna do them on the other side. So we're gonna do the same 4 problems without replacement. I'll give you a couple minutes to go through and do that. If you need me, wave your hand. All right, so for each of these probabilities that we do, the first one's going to be the same. It's what's going to be different, what we're going to have to talk about if there's any questions, is what happens with the second one, because we're now doing this without replacement. So when I find the probability of 2 3s, well, the first card being a 3 is still going to be 4 out of 20. That does not change. But now here's the assumption you made. I've pulled a 3 out. Okay, because we assume the first one's a 3 and then another 3. So now how many 3s are left in the deck? 3 out of how many cards? Great job. You're doing excellent. So 4 times 3 is 12 divided by 20 divided by 19. What decimal is that? 0.0316. Do you have agreement on that? We feel good about it? Okay. I'm going to keep going. Lion and then a monkey. So again, the probability I get a lion is still going to be the same. It's going to be 5 out of 20. But this time I'm not replacing the lion. I have a lion in my hand. What's the probability now that I draw a monkey with the next one? How many monkeys are there? Yeah, that doesn't change. How many cards are there? That's what changes. 19. Yes. So 5 times 5 is 25, divided by 20, divided by 19, and that turns out to be point what? 0.658. Frog and a yellow bird. Well, again, the frog, probably a frog does not change. There's 5 frogs out of 20. Now I'm holding a frog in my hand. I'm going to pull again. What's the probability of a yellow bird now? 2 out of 19. Excellent job. 5 times 2 is 10, divided by 20, divided by 19. Turns out to be 0.0 what? 268.3. Thank you. And last but not least, both are even numbers. The first one being even is 8 out of 20. Fantastic. Times, and now I'm holding an even number in my hand. What's the probability the next one's an even number? 7 out of 19. So 8 times 7 is 56, divided by 20, then divided by 19, and that turns out to be 0.1474. Everybody feel all right about that? All right, we just got a couple more examples, just because I want to drill this home so that you do amazing on it on the test that we have coming up. So example 7, this time instead of cards, we're spinning a spinner, but the premise is exactly the same. So I want you to do the A, the B, the C problem, spinning that spinner. All right, so when I spin this spinner, if you remember, we've seen this spinner once before in previous problems. This was a long time ago, so I don't blame you if you don't remember. So if you're wondering how to deal with the spinner, remember, we are doing probability with equally likely outcomes. You can say, okay, half this is green and the quarter's red, quarter's yellow. But if you draw this little line right here, now you've got equally sized spaces and you can just count up the number of spaces. Either way you want to approach this, it doesn't matter. So here we go. What's the probability that I get a red on both spins? Okay, well, I spin the spinner. What's the probability it lands on red the first time? 1 out of 4 or 0.25 if you're using decimals. What's the probability it lands on red the second time? 1 out of 4 again, or 0.25 if you're using decimals. So that is, if you want to just multiply, 1 out of 16. And 1 out of 16, I believe, is 0.0625. Awesome. Thank you for helping me out. We okay with that? Okay. Green and then yellow. So the probability it lands out of green is 2 out of 4 or 0.5 if you're using decimals, because half the area of that spinner is green. And then the yellow is 1 part out of 4 or 0.25. So that is 2 out of 16. And 2 out of 16 is let's see, that's 1 out of 8. That's 0.125, I believe. And then last but not least, I asked you just to do the thought problem. Well, this time, if we're not going to spin it twice, we're going to spin it 3 times. What's the probability that I get 3 reds? Okay. The whole point of this problem is just to let you know that and events, you can string along any number of events. You could do it 100 times. Okay. And that would be the probability. Okay. So what's the probability it's red on the first one? 1 out of 4 or 0.25. And then the second one, 1 out of 4, 0.25. And then the third one, 1 out of 4, 0.25. And so now you have 1 chance out of 64. Okay. So you can see it gets less and less likely the more times you do it. So 1 chance out of 64 turns out to be 0.0156. We'll round it to the 4th decimal place and we're done. All right, we're just about done with this section. One more problem. Okay, it's Friday night. You want to watch a movie, and on a shelf you've got 7 DVDs if you still own such things. There's 4 dramas. There's 2 science fiction. There's a comedy. 2 movies. You're going to select 2 movies at random. And you're going to do the following. You're going to determine these probabilities. So you're going to do it both. I'm going to just draw a little wall right here. You're going to do it with replacement. I'll put the word with right here. And then you're going to do it without replacement. There's 2 problems. You're going to do with and without, just to round out our discussion of and problems. All right, so the first time I go through this, I'm going to do this with replacement. So first I want to find the probability of a drama and then a comedy. So when I reach my hand onto this shelf, maybe I can't see where the movies are. What's the probability I come away with a drama the first time? Yep, there's 4 dramas out of 7. That's great. Times, well, maybe I didn't want to watch a drama, so I put it back up on the shelf. Now, what's the probability the second one comes out a comedy? Okay, 1 out of 7. Great. So that's 4 chances out of 49. And rounded to the 4th decimal place, that's 0.0816. So far, so good? If you have any questions at all, please ask them. We got plenty of time. We're doing great. Okay, 2 comedies. Okay, well, when I reach my hand up, you already told me the probability of a comedy is 1 out of 7. Then I replace it because maybe I wanted something different. Now, what's the probability that the next one's a comedy? It is also 1 out of 7. Great, because we are replacing. And so that's 1 chance out of 49 that both times you have a comedy, and so that's 0.0204. All right, we're going to finish up by doing these same 2 things without replacing the movie once I've drawn it. So first one without replacement, drama and comedy. Well, the drama is not going to change. It's still 4 out of 7. But now I'm keeping the drama, whatever it is, and I'm reaching my hand up again. And what's the probability the next one is a comedy? Yeah, now there's still 1 comedy up there, but now there's just 6 movies. So that's 4 out of 42. And that's 0.0952. And last but not least, 2 comedies. Well, I reach my hand up. The first one being a comedy is 1 chance out of 7. I'm now holding that comedy in front of my hands. And now I reach my hand up. What's the probability the next one comes down a comedy? Yeah, there's no more comedies up there. There's 0 out of 6. So 0 times anything is 0. And then for the sake of review, from our basic probability facts, what does it mean when the probability of something is 0? Can't happen.